ladies and gentlemen, this is Mrs. Jackson, and I'm going to walk you through some of the basics of nuclear chemistry. We're going to talk about what nuclear chemistry is, how to write nuclear decay reactions, and we're going to compare it to the chemical processes that we will look at most of the school year. So let's start by looking at the difference between chemical processes and nuclear processes. Chemical processes are the things that most people think about when they hear chemistry. These are the things that are things like fire or explosions or things that happen in the beakers and the flasks that change color and form bubbles, and they look like science to a lot of kids, and it's what kids imagine as chemistry. Well, those are all chemical processes, and those are all driven by what the electrons in the cloud are doing, okay? So because we're talking about electrons with a chemical process, we're not talking about the nucleus. Electrons drive chemical processes. Nuclear chemistry, the word even looks kind of like the word nucleus. Nuclear chemistry is all about what the nucleus is doing, okay? When you have a nucleus that's either too big or it has too many protons to be stable, or it doesn't have enough neutrons to be stable, we get an unstable nucleus. An unstable nuclei cannot stay together. So we start looking at changes in that nucleus, and that's what drives nuclear chemistry. So where electrons drive chemical processes, the behavior of the nucleus is going to be what drives nuclear processes. In chemical processes here on the left, because everything is happening in the electron clouds, the nucleus doesn't change, and so my elements remain exactly the same. They may bond, right? They can lose electrons, but because their nucleus doesn't do anything or doesn't change, the element stays the same. On the right-hand side, when a nucleus is unstable and radiation has happened, that nucleus changes. And when that change happens in the nucleus, I very often will have different elements when I'm finished with a nuclear process than when I began. So because nuclear processes occur in the nucleus with protons and neutrons, they very frequently result in the formation of a different element. Chemical processes happen with the electrons, and they do not cause a change in the elements. They just will change who they bonded to, or they might change their charge. So those are the differences. Nuclear chemistry is what we're studying now. Chemical processes will be what we study for the remainder of the school year. So let's start looking at why nuclear changes happen. Okay, let's start talking about a few key terms that you need to be able to define. We're going to look at radiation and radioactivity, which are very similar in the way they sound, and they're similar because they're related to the same thing, but they're not the same thing. Radiation are the particles. Radiation are the particles that are emitted. So as we learn about some of the particles here in just a few minutes, that's going to be the radiation, those rays or particles that come apart or come out of a nucleus when it begins to decay. Most of you have heard of decay before. Decay is when something falls apart, and that's what happens when radiation is emitted. Emitted means to be given off. Okay? Radioactivity is the process of decay of a nucleus. So it's a process. When that unstable nucleus breaks down or decays, it gives off particles, and we call the particles radiation. Radioactivity is the process. Particles or radiation are the particles that come from that process. So when you have a big unstable nucleus, it can't stay together, so it comes apart. That is radioactivity. Sometimes they're so big and so unstable that they have to come apart step by step by step. We call that series, or those steps, a decay series. So it doesn't decay all at once. It may have to happen in several steps. Sometimes that takes seconds, sometimes it takes hundreds of years. It all depends on the element itself. Be sure that you have these definitions down on your note guide before you move forward to the next part of the lesson. All right, so how do we know when a nucleus is unstable? So you need to get two things down. There's two things that really drive the stability of a nucleus. One of them is going to be the ratio, right here, the ratio of neutrons to protons. So for small atoms, 1 neutron for every proton is stable, and that usually is up through about element number 20, calcium. And that usually is where you see that 1 proton for every neutron ratio. Think about what you know about protons and neutrons already. Protons are positively charged. And if you've ever played with magnets or learned anything about magnets, you know that magnets have two ends. They have one they call a positive side or a positive end or pole, and they have a negative. And opposites attract, and so if you have two opposite ends of a magnet, they will come together in a snap. But if you have the same end of a magnet and you try to push it together, they don't want to come together, and you have to really push. The same is true of protons in the nucleus. If I have an awful lot of protons that are all the same positive charge and I try and push them together in the nucleus, they do not want to stick together. So it takes an extraordinary amount of energy to hold them together. And that's why nuclear processes have so much energy associated with them. If you think of nuclear chemistry, sometimes people think of a nuclear reactor or a nuclear bomb. Lots and lots and lots of energy. That's because it takes a lot of energy to keep those positive protons all together. So those neutrons play a role in that. They help to space them out. So the first thing that you need down for stability is the neutron to proton ratio. The other thing is the number of particles in the nucleus. Okay? The greater the number of particles in the nucleus, protons in particular, the more unstable it is. So if I have a tiny atom with just 3 protons, it's going to be more stable than a very large atom or nucleus like uranium with 92 protons. So we've got the neutron to proton ratio and the total number of particles in the nucleus, particularly protons. The bigger they are, the more unstable they will be. All right, so let's start looking at what happens to this unstable, if you look right here, this really unstable nucleus. You can see that the picture is kind of broken apart. So what does that look like? We're going to look at several different types of radiation. We're going to look at several types of decay or processes where the nucleus comes apart. And we're going to look at some bigger processes like fission and fusion. So be sure you've got your note guide ready to go. The examples on your note guide are going to be exactly what you see here. So you can get down the same examples and it's going to look just like the video. So for the 3 common types of radiation that we discuss, we're going to look at alpha, beta, and gamma. Okay, I'm going to look at each one of these in detail. You can see here that we've got the 3 symbols. I've got an alpha symbol here, a beta symbol, and a gamma symbol below. And I'm going to look at each one of those separately. So don't panic just yet if you haven't gotten all that down. We're going to look first at alpha. So this symbol here is the Greek letter alpha. Okay, this is the Greek letter alpha. It is also, an alpha particle will also be represented by the symbol or the element symbol for helium. Because, as we're going to look at here, an alpha particle is a helium nucleus. So helium is element number 2. Okay, so helium, here's an example of one way you can write an alpha particle. Helium nuclei have 2 protons. That's what makes it helium. And that's how I know to use the helium element symbol. The mass number of this helium nucleus is 4. So this particle has 2 protons and 2 neutrons. But it has a positive charge, and that tells me it's had both its electrons removed. So it has lost 2 electrons. So this is one version of the alpha particle symbol. You can also write it in a different way using the alpha symbol. The alpha symbol from the Greek alphabet looks like this. Okay? But you also have to include the atomic number 2 and the mass number 4. You can use either of these two symbols when you write your equation notations, but you need to recognize both of them. You can pick your favorite and use it again and again, but you should recognize both of them. So let's take a look at how a decay equation works. You kind of need to think of this along the lines of the law of conservation of mass. Mass isn't created or destroyed, but it can change forms. So when I look, I've got two sides of any chemical process. I've got the before and after. The before is called the reactants, and that's on the left. So on the left-hand side of my equation, these would kind of, oh my stars. Okay, on the left-hand side, these are going to be where I start on this side, and then on the left-hand side, okay, is going to be the ending. So we've got reactants essentially on the left, products on the right. So when I look at my mass numbers are on the top. The mass number on the left is 235. Whatever is on the final side, or the product and right-hand side, has to equal 235. So this first particle, thorium, has a mass of 231. And when I add to that the mass of the alpha particle, which is 4, 231 plus 4 equals the 235 on the left. So that piece is completed, and that is equal. That follows the law of conservation of mass. On the bottom side, I have the atomic number 92 when I started. At the end, it has to still equal 92. So I've got 90 plus 2 does equal the 92 I began with. And we're going to follow that same process for all of our nuclear decay equations. The top has to be equal on both sides, and then the bottom value has to be equal on both sides. Now let's do a couple of examples. I've got actinium here as my starting material. I see that it's going to undergo an alpha decay, and I need to figure out what particles go in each one of my boxes. So because I know it's alpha decay, the first thing that I'm going to do is I'm going to write the 4/2 for my alpha particle, and I'm just going to use the alpha symbol. You can use the helium element symbol if you prefer, but this is just as good. Now I need to figure out what goes in the last box. Remember that my left-hand side started at 221, so when I'm finished, my right-hand side should have 221 also. So 221 is my target. I have 4 as my mass for the alpha particle. So what do I add to 4 to make it 221? The answer is 217. Okay, so 217 is my mass number on top of this particle. Let me write that a little bit more easily so it can be more easily read. So there's my 217. Now I have to determine what number is going to go in the bottom. So I've got 89 as the target on the left, and I've got 2 protons in the alpha particle. What do I add to the 2 so it equals 89? And the answer is 87. To figure out what element that is, I know that 87 is its atomic number. I look at the periodic table, and the element with the atomic number of 87 is francium. And so I write Fr as my element symbol. And it's as easy as that. It takes practice, but it's really just addition or subtraction. So let's continue with 2 more examples, and then we'll move on to beta decay. Francium 217 is my next particle. Again, I see it's undergoing alpha decay, so I know that my first particle is going to be an alpha particle, so I've got 4/2, and I know it's a helium nucleus. Right, now I have to figure out my second particle. 217 is the target on the left. What do I add to 4 to be 217? The answer is 213. And then on the bottom, the target is 87. 2 plus 85 matches 87. 2 plus 85 is 87. Then I look up 85. as my new element, and I have astatine, which is an AT symbol. Final example, I'm starting with the astatine at the bottom. I see again, it is alpha decay, so I start with my alpha particle. Okay, 213 is the target on the left. 4 plus 209 is my missing particle here. 85 is my target on the bottom. Okay, 2 plus 83 is my number for the bottom. I look up element number 83. I see that it is bismuth. I put in the symbol and I am finished. So again, simple math, but it does take some practice, which you will get from your instructor. All right, let's look at the next type of decay, which is, it is called beta decay. Now this is a little different because we're going to work with some negative numbers. Beta particles are essentially an electron. And so electrons do not have any mass. So they have a mass of 0, but they do have a negative charge. So they're going to be opposite of a proton. So to write the beta particle, you can either use this Greek symbol beta, or you can use the symbol that we use for an electron. You have a little e, you've got a 0 on top because it has no mass, and then you put the -1 in the bottom because it is the opposite of a proton. It carries a negative charge. So here's an example of lithium-8 undergoing beta decay. So here is, again, remember decay is coming apart. So I am starting with lithium-8. And again, here's my middle. That's my dividing line between what I start with on the left and what I finish with on the right. When I look at this equation, it's going to work in the same way. I know that I have a beta particle, and I always write it first. This example has it written second, but I always write mine first. I'll show you in just a flash. So when I look at the top numbers, 8 is equal to 8 plus 0. So it works the same way that the alpha particles did. The bottom number is 3, so the target is 3. Okay. This particle is a positive 4. So positive 4 plus -1 or -1 equals 3. 4 plus -1 is a positive 3. So it's similar, but it is not exactly the same. So let's look at how this fills in like the alpha did. So I've got strontium 90. I know that this one's going to undergo beta decay. You will be told what type of decay you need to write. I'm going to write my symbol for beta particles first. So I have 0 and a -1, and I'm just going to use the E on this example. So the top number is pretty easy. What do I add to 0 to make it equal 90 on the left, which is my target? Well, that's easy. That's a 90. Okay, and what do I add to a -1? Or what do I subtract a 1 from to get 38? Well, the answer is going to be 39. 39 minus 1 is 38. Okay, let's do another example. Neptunium 239. So I'm going to write the symbol for my beta particle here, 0 over -1, and I'm going to use the beta symbol on this one. The top number, remember, has to be the same. 239 is equal to 0 plus 239. And then in the bottom, I have to figure out my new value here. So I have something plus -1, which is really subtracting 1. So what do I take 1 away from to equal 93? The answer is going to be 94. 94 minus 1 is 93. Americium, same idea. Beta particle here, 0, -1. There's my beta particle. 0 plus 247 is going to equal 247 on top. And then 95, I have to have 96 plus -1 or -1 matches my 95. Oh my goodness, I have not filled in any of my symbols. Let's look up this problem first. 96, that element is going to be curium. I apologize for that. There's curium. When I come back and I look at element number 94, this is plutonium. When I look up element number 39, that is yttrium. All right. Last example, bromine 82. I'm going to put my symbol for my beta particle in, and then I'm going to fill in my other blanks. The top number is easy, 82. And then I have to figure out the bottom. What minus 1 is 35? The answer is going to be 36. When I look up element number 36, that is the noble gas krypton. And that's how you work the beta decay problems. You're still trying to make the left match the right on the top and the bottom. All right, the next one's super easy. It is called gamma radiation. Now, gamma radiation is pure energy. This is the symbol for a gamma particle. It's a Greek symbol, gamma. Looks like a funny Y. It has no mass and it has no charge. And so its presence, if you look here, does not change any of the things we've looked at so far. It does not generally stand alone. Normally you will see gamma radiation released with other decay. So here is the gamma particle being emitted with this guy we just looked at. This is our beta particle. In the bottom example, here's another gamma particle being emitted with alpha radiation. So the gamma doesn't exist by itself, but it will usually accompany the alpha or the beta radiation. So if you've got a blank or you've got a particle and you already have the numbers and they match, you're probably looking at gamma decay. Lots of energy, very dangerous radiation. All right, the next and fourth piece or particle that we're going to talk about, it's called a positron. It's a positive electron, or you can think of it as the positive charge off of a proton. So let's look at positron emission. It's like losing a positive charge. So my positron particle looks like this. I've got 0 over a positive 1. Okay. Notice I'm still using that E. You could also use the beta symbol as you do here. So you can have no mass, positive charge with the E for the positron, or you can have no mass, positive charge, and the beta symbol. It's a positive electron. So if I know that cobalt 54 is going to undergo positron emission, I write that first. No mass, positive charge, and then my E. The top number, what plus 0 equals my 54 target. That's easy. It's a 54. On the bottom, what do I add to a positive 1 to make it 27? That is a 26. 26 plus 1 equals 27. Element number 26 is iron. Zinc. Okay, next example, our zinc 61. If it's undergoing positron emission, here's my positron particle. That's a positive sign and a 1. For my top value, there's my dividing line. 61 is the target. 0 plus 61 matches 61. Then I have positive 1 plus 29 equals my target of 30. Element number 29 is copper, Cu. And then lastly, gallium 68. If it's positron emission, I'm looking at 68 for my mass number and a 30 for my atomic number. And that makes this element 30 is zinc. 30 plus 1 is 31. And that's your positron emission. So we're following the same process for all types of decay. The last type of simple decay process that we're going to look at is called an electron capture. Notice this is being captured. So I'm not giving this off. I'm not emitting it. I am capturing it. So the nucleus with all of its positive charge. Remember, protons and neutrons in the nucleus. Protons are positive, and they're going to capture an electron. They're going to pull it in. And this is the only one where we write the particle on the left-hand side. So here is my nucleus over in this example, and it's going to capture that electron. And when it does, that electron is going to cancel out a proton. So let's see what this looks like. So here is cobalt-57 undergoing electron capture. Again, here's my dividing line. Okay, and the left-hand side still has to equal the right-hand side. So 57 plus 0 is 57 for the top. And then on the bottom, I need to figure out what value is going to be my atomic number in the bottom. So 27 plus -1, or 27 minus 1 is 26. I look up element number 26, and that is iron. Next example, we have our arsenic. One more. We've got arsenic here, arsenic 73. This is electron capture. Notice it's on the left-hand side. This arsenic captures that electron. So it has no mass, so my particle still weighs 73, or has a mass of 73. But I neutralize one of my protons. So 33 minus 1 is 32. That negative electron canceled out one of my protons. Now I have element number 32, which is germanium, Ge. And then lastly, in barium-128. Again, electron captures on the left. 128 plus 0 is 128. And then 56 minus 1 is 55. And 55 is cesium. Element 55 is cesium, or Cs. And that's your electron capture. It's the only one that goes on the left, so he's the only one that's a little bit different. The last two pieces we're going to look at are probably what most people think of when they think of nuclear chemistry, and that is fission and fusion. All right, and both of these are very important in the world today. They have a lot of applications, but they are different processes. In fact, they're almost opposite processes. So one of the things that I like to show my students is with the vowels in the word. Fission is when a nucleus comes apart. So this is what we looked at for some of those early atomic bombs in the 1940s. Fat Man and Little Boy were the names of the bombs that they developed in the Manhattan Project toward the end of World War II. And so when we look at fission, fission is when a nucleus splits into smaller nuclei. So here you can see I've got this big nucleus right here. Really big nucleus, probably not stable. And I have to get the process started. So usually you'll see a neutron crash into that nucleus that was already unstable. Well, when that neutron crashes in, makes it so unstable it can't stay together, it splits. And when it splits, I get two smaller nuclei, and then I get some additional neutrons that get kicked out. And those neutrons go on and crash into another unstable nucleus. And each one of those unstable nuclei is going to split just like the one we started with, and they eject 3 more neutrons. And when that continues to happen, we call that a chain reaction. And that's what detonated some of those early atomic bombs. Fission is when they split into smaller nuclei. So that those vowels may help you. Fusion, by comparison or by contrast, fusion is still in the nucleus, right? So that's what they have in common. Okay, but fusion is when I bring small nuclei together. So when I start with 2 smaller particles and they come together to form a bigger one, we call it fusion. Fusion is where we unite our nuclei, like on the sun. Okay, so those 3 vowels may help you. Fusion is when we unite nuclei